Tonight we're going to explore one of the strangest properties of the ocean. A property so quiet, so invisible, and so thoroughly outside the range of what most people think about that you have probably lived your entire life without noticing it. The fact that the ocean carries sound, not in the way you hear a voice across a room, or a car passing on a distant street, or a wave breaking on a beach at night, but in a way that reaches across whole oceans. A way that allows a single low note, released somewhere off the coast of California, to be heard by a listener on the other side of the Pacific, more than a week of steady sailing away. The ocean is not just a place full of water and creatures and currents and slow geological processes. It is also, and perhaps primarily, a sound. A continuous, immense, multi-layered sound. Reaching across distances that no human voice on land could ever hope to cross, carrying information and calls and cries and groans through the dark, in ways we are only beginning to understand. By the end of tonight, you're going to understand why sound is the true medium of the deep ocean, in a way that light never could be. Why there is a narrow layer of water, roughly a kilometer below the surface, where sounds become trapped and can travel for thousands of kilometers almost without fading, and why the creatures of the deep, the whales, the fish, the invertebrates that we know, and the ones we have never seen, live inside an acoustic world so vast and so interconnected that our own world, full of speech and music and the constant chatter of human voices, would seem to them cramped and strangely silent by comparison. Before we get started, if you love exploring the depths of the ocean as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something you already know, at least in a rough way, and then slowly pull apart the assumptions underneath it. Sound, in the world you live in, travels through air. When you speak, you push a small wave of pressure through the air in front of your mouth, and that wave reaches the ears of anyone standing near you, who then interprets that wave as a word. Sound on land is a thing of short distances and quick decay. Your voice fades within a few meters. A shout carries maybe a few hundred. A gunshot, if the air is still and the terrain is open, might reach a few kilometers. But even then it arrives as a small distant crack barely distinguishable from a branch snapping. The air is a poor conductor of sound. It is thin, easily disturbed, and full of obstacles, trees, buildings, hills. Moving currents of warm and cold air that scatter and absorb acoustic energy almost as quickly as it is released. In the world above the waves, sound is a local phenomenon. It belongs to the space around you, and very little of it reaches beyond. But the ocean is not air. The ocean is a dense, continuous fluid medium, roughly 800 times denser than the atmosphere you are breathing right now. And this density changes everything about how sound behaves. When a sound is made underwater, it does not push through a thin, scattered medium. It pushes through something closer to a solid, a packed, coherent body of water whose molecules are so tightly arranged that a pressure wave moving through them loses very little energy to friction or dispersion. Sound travels, in seawater, at roughly 1,500 meters per second. That is about 4.5 times faster than sound travels through air, where the speed is only about 340 meters per second. A single second of underwater sound covers a distance that would take 4.5 seconds of travel in the air you are used to. And because the ocean is vastly larger than the air column of any single terrestrial space, because it has no walls, no hills, no buildings, no scattering obstacles above the seafloor, A sound that enters the water in the right place and in the right way can propagate for distances that would be unimaginable in the world above. This is the first thing to understand. The ocean is, in a very literal sense, a much better medium for sound than the air around you. If you were submerged in water and someone 100 meters away clapped their hands, you would hear that clap as clearly as if it had happened next to you on land. If they clapped from a kilometer away, in the right conditions, you might still hear it. And if the sound was loud enough and low enough in frequency and emitted at the correct depth, you could hear it from thousands of kilometers away. From the other side of an entire ocean basin, through water that had never been disturbed by that particular sound before reaching you as a clear, recognizable pulse, as though the event had happened much closer. This is not a theoretical property. It is a real, measurable, directly observed feature of the planet we live on. And once you begin to understand what it means, the way you think about the ocean starts to shift. Because if you can see only a few meters ahead of you underwater, but you can hear for thousands of kilometers, then the dominant sense of any creature that lives beneath the surface, the sense that carries the most information about the world, the sense that reveals the greatest range of experience, is not vision, it is hearing. The ocean is, fundamentally, an acoustic place, and everything that lives in it, everything that has evolved to depend on it, is shaped by that fact. Now let's go deeper into the physics, because the way sound moves through the ocean is stranger and more beautifully structured than the simple description so far has implied. The speed of sound in seawater is not constant. It changes depending on three factors: temperature, pressure, and salinity. And of those three, temperature has the largest effect. Warmer water conducts sound faster than colder water. Deeper water, where pressure is higher, also conducts sound faster. Salinity matters, but less than the other two. And in the open ocean, the salinity is relatively stable from place to place, so its effect is small. What this means is that as you descend through the ocean from the surface to the seafloor, the speed of sound changes with depth, and it does not change in a simple, monotonic way. It rises, it falls, and at a specific depth it reaches a minimum, a point where sound travels more slowly than at any other depth above or below. At the surface of the ocean, in temperate latitudes, the water is warm, and sound travels through it at roughly 1.52 to 1.540 meters per second. As you descend, the water cools rapidly through a layer called the thermocline, and the speed of sound drops accordingly. By the time you reach a depth of several hundred meters, the water has become cold and stable, and the speed of sound has dropped to around 1.480 meters per second or lower. But then, as you continue downward, pressure begins to dominate. The water below the thermocline stays at nearly the same cold temperature all the way down, but pressure keeps increasing, and that rising pressure causes the speed of sound to rise again. So there is a specific depth, somewhere between 800 and 1.200 meters, in most mid-latitude oceans, where the speed of sound reaches its minimum, just before pressure takes over and starts pushing it back up. This layer of minimum sound speed has a name. It is called the sound fixing and ranging channel, or SOFAR channel, and it is one of the most remarkable features of the ocean you have probably never heard of. The SOFAR channel is a horizontal band of water, roughly a kilometer below the surface, where the physics of the ocean conspire to produce an acoustic waveguide, a natural conduit through which sound can travel enormous distances with almost no loss of energy. And it exists, in one form or another, in every major ocean basin on Earth. Here's how it works. When a sound wave is produced inside the SOFAR channel, the wave begins to spread in all directions, the way any sound wave does. But as parts of the wave travel upward, away from the axis of the channel, they enter water where the speed of sound is higher. Because sound waves bend, they refract toward regions of lower sound speed. The upward traveling parts of the wave are bent back down toward the channel axis. And the parts of the wave that travel downward into the deeper, higher pressure water are also in regions where the speed of sound is higher, so they too are bent back toward the axis. The sound wave, instead of spreading in a sphere the way it would in air, becomes trapped. It oscillates up and down across the channel axis, curving back and forth, unable to escape either upward or downward, for as long as it has energy to travel. And because the sound wave never hits the surface of the ocean, where it would scatter and be reflected in complex ways, and because it never hits the sea floor, where it would be absorbed by sediment, it travels almost horizontally, losing energy only very slowly through absorption in the water itself. At the low frequencies that whales and other large marine animals produce, absorption in seawater is minimal. A sound of 10 or 20 hertz, deep slow below the range of human hearing, can travel in the SOFAR channel for thousands of kilometers before it fades below the background noise of the ocean. Think of it like a fiber optic cable, buried a kilometer below the surface of the sea, running continuously around the entire globe. Light in a fiber optic cable bends back toward the core of the cable whenever it tries to escape, and so travels in long, smooth, nearly lossless paths over enormous distances. Sound in the SOFAR channel does exactly the same thing, except the channel is made of seawater, and the waves are acoustic rather than optical, and the distances involved are not measured in the meters of a cable spool, but in the width of oceans. The SOFAR channel was first discovered, or rather first understood as a discrete feature, in the 1940s, independently by two different teams of physicists. One was led by an American oceanographer named Maurice Ewing, working at Columbia University. The other was led by a Soviet physicist named Leonid Brekhovskik. Both teams were investigating long-range underwater sound propagation for military reasons during and just after the Second World War, and both arrived at the same conclusion. There was a layer in the deep ocean where sound became trapped and could travel almost indefinitely, and if you put a hydrophone at the right depth, you could detect sounds from almost any part of the ocean. Ewing's team demonstrated this dramatically in a series of experiments beginning in the late 1940s, in which small explosive charges were detonated at the channel depth near Bermuda and Bahamas, and the resulting pulses were clearly recorded at listening stations thousands of kilometers away off the coast of West Africa. The explosion was small. The signal, by the time it arrived at the far hydrophone, had traveled for more than an hour across the Atlantic Ocean, and it was still recognizable, still identifiable, still carrying the unmistakable acoustic signature of its origin. That experiment, and the dozens that followed, confirmed something that is easy to say, but hard to fully appreciate. A sound made in one part of an ocean, at the right depth and the right frequency, can be heard in any other part of the same ocean. The acoustic reach of the sea is not limited by horizon or distance in the way the acoustic reach of the air is. It is limited only by the energy of the source, the frequency of the signal, and the background noise of the environment. A loud enough, low enough sound, released into the SOFAR channel, can be detected on the far side of the planet. The ocean is, acoustically, a single connected space, and for as long as life has existed in that space, every creature that lives there has been living inside a medium where distant events can be heard clearly, where neighbors are never really out of earshot, where the whole world is in some sense always audible. Keep going, because this is only the first feature of the acoustic ocean, the foundational physical fact on which everything else rests. The SOFAR channel is what makes long-distance underwater sound possible. But it is the creatures that live in this acoustic world, the animals that have evolved over tens of millions of years to take advantage of it, who have turned it into something genuinely extraordinary. Let us talk about the whales. When people think of whales, they usually think of the visual animal, the enormous body breaching the surface of the sea, the dark fluke rising out of the water, the misty spout of a blow. That is the whale you see in documentaries and on whale-watching boats, the whale that tourists travel to see and that photographers frame against the horizon. But the visual whale is in a way the smallest part of what a whale actually is, because whales are primarily acoustic creatures. They live most of their lives in dim or total darkness, far below the surface, where vision is limited to at most a few meters of murky blue haze. Their main sense of the world is hearing. Their main tool for interacting with each other is sound. And the sounds they produce are so powerful, so finely tuned, and so specifically adapted to the physics of the ocean that they turn the individual whale into a kind of acoustic broadcasting station, capable of reaching other individuals across distances that would take weeks to swim. Consider the blue whale. The blue whale is the largest animal that has ever existed on Earth. It is larger than any dinosaur whose skeleton we have ever assembled. An adult blue whale can reach a length of 30 meters, about 100 feet, and weigh more than 180 tons. Its heart alone is the size of a small car. Its tongue weighs as much as an elephant, and when it opens its mouth and produces a call, it produces one of the loudest sounds ever measured in any living animal. A blue whale call can reach 188 decibels, measured at the standard underwater reference pressure. To give you a sense of what that means, a jet engine at takeoff, measured in air, is somewhere between 125 and 155 decibels. The blue whale's call, measured as a pure sound pressure level, is far louder. And it produces this sound not in short bursts, but in long structured sequences, moans and pulses and low rumbles, lasting for 10 or 20 or 30 seconds, each repeated at intervals that can go on for hours. The frequency of a blue whale's call is extraordinarily low. Most of the energy is concentrated around 10 to 25 hertz, which is at the very bottom of what the human ear can hear, and in many cases actually below it. If you were in the water next to a calling blue whale, you would feel the sound more than you would hear it. Your chest would vibrate. The water itself would pulse around you in a rhythm so deep and so powerful that it would seem to originate from inside your own body, rather than from the animals several meters away. But the fact that the sound is so low in frequency is not a coincidence, and it is not a limitation. It is precisely the property that allows the sound to travel as far as it does. Because low-frequency sounds in seawater are absorbed much less than high-frequency sounds. They lose less energy per kilometer. They penetrate further, they persist longer, and they remain recognizable at distances where higher-frequency sounds would have long since faded into the background noise of the ocean. The result is that a blue whale's call, made near the SOFAR channel and propagating through its acoustic waveguide, can travel for hundreds, and under the right conditions, thousands of kilometers. Scientists have measured blue whale calls detectable across distances of more than 1,500 kilometers, nearly 1,000 miles, and there are theoretical reasons to believe that, in very quiet ocean conditions, without much human-generated noise, blue whale calls could be heard across entire ocean basins, reaching other whales thousands of kilometers away. This was first seriously proposed by Roger Payne, the oceanographer who also discovered that humpback whales produce what we now call whale songs. In the early 1970s, Payne and his collaborator Douglas Webb calculated, based on the acoustic physics of the ocean, that the low-frequency calls of the largest whales could in principle be heard across thousands of kilometers of water. Their calculation suggested that two blue whales, on opposite sides of an entire ocean, could communicate with each other through the SOFAR channel if the water between them was quiet enough. They could, effectively, have a conversation at planetary scale. For a long time, this idea was treated as speculative, but the evidence has steadily mounted. Blue whale calls have been detected at enormous distances by widely separated hydrophones. Patterns in the calls suggest that individual whales time their vocalizations as though they were aware of being heard at great distances. And the population structure of blue whales, the way the calls differ between different regions like dialects between different countries, strongly suggests that whales across ocean basins do in fact hear each other regularly enough for their vocalizations to be shaped by shared acoustic traditions. The blue whale, in other words, lives in an acoustic world so vast that the entire ocean basin is, to its ears, a single room. Take a moment to sit with what that means. For a blue whale, the distance between California and Hawaii is not a separation. It is a medium. The roughly 4,000 kilometers of open Pacific between those two places are not empty space. They are a conduit, a passage through which voices move, continuously bringing news of other whales, other individuals, other events, in a kind of continuous low-frequency chorus that goes on day and night, year after year, for the entire lifespan of the animal. A blue whale never loses contact with its kind. It never experiences the kind of isolation that a single creature would experience on land, where every individual exists within a small acoustic bubble defined by the limits of air. For the blue whale, isolation is not a matter of physical distance. It is only a matter of silence. And silence, in the ocean, is rare. And still, we have not reached the strangest part of the acoustic ocean. Because the blue whale is not alone in using the ocean as an acoustic medium. It is only one of many species that have evolved, over tens of millions of years, to live inside the sound of the sea. And some of the others are even stranger, even more finely adapted, even more precisely tuned to the physics of underwater acoustics than the blue whale itself. Consider the fin whale, the second largest animal on Earth after its blue cousin, reaching about 24 meters in length and weighing up to 70 tons. Fin whales produce a call that is so loud, so consistent, and so precisely tuned to the physics of long-range propagation that for decades, when the first hydrophones picked it up, scientists could not figure out what it was. The call is a simple pulsed, low-frequency note, centered on about 20 Hz just below the lower edge of human hearing, and it is repeated at regular intervals, sometimes for hours or even days without pause, in sequences that stretch across entire nights. The 20 Hz pulse of the fin whale is produced at a source level estimated to be somewhere between 186 and 190 decibels, which places it roughly equal to the blue whale in terms of acoustic power. And because it is almost perfectly matched to the frequencies that travel best in the SOFAR channel, it propagates across enormous distances with very little loss of energy, reaching other fin whales hundreds or thousands of kilometers away. For a long time, before scientists understood that these were whale calls, the 20 Hz pulses picked up by military hydrophones during the early Cold War were a mystery. The pulses were too regular, too consistent to be random environmental noise. They were too slow, too rhythmic to be mechanical. They did not fit any known pattern of geological activity. There was even speculation. In the 1950s and early 1960s, that the sounds might be coming from Soviet submarine tests, some new kind of sonar or communication system, because there seemed to be no natural explanation for why something so loud and so precisely periodic would be echoing through the ocean at these low frequencies. But here's what the analysts did not yet realize. The mysterious 20 Hz pulses were not mechanical at all. It was only in the 1960s, when American researchers began analyzing the signals more carefully and correlating them with the known distribution of fin whales in the Atlantic, that the truth became apparent. The pulses were biological. They were the calls of fin whales, communicating across the open ocean, and they had been going on for as long as fin whales had existed, for millions of years. The Soviet submarines the analysts had briefly feared were, in reality, fin whales, singing their regular pulsing songs through the SOFAR channel, broadcasting their presence to the entire basin. Consider what that means. There are sounds in the ocean so loud and so regular that when humans first built the equipment to hear them, we mistook them for man-made devices. We assumed that only something with the industrial power of a submarine could be producing that kind of signal. But it turns out that the ocean had been producing those signals through the voices of its largest animals for longer than humans had existed as a species. What we thought was novel and mechanical was in fact ancient and biological. We had just finally built the ears to hear it. Now let's move to the humpback whale, because the humpback takes the underwater acoustic world in a different direction entirely. The humpback is smaller than the blue whale or the fin whale, about 15 meters long at adult size, weighing around 30 tons. And it does not produce the same kind of low-frequency, long-range calls. Instead, the humpback produces what has come to be known, in both scientific and popular language, as song. Humpback songs are the most complex vocalizations produced by any non-human animal. They are structured like human music, with identifiable themes, phrases, and repeated patterns. A single song can last anywhere from 10 minutes to half an hour and is composed of sequences of notes, some low, some high, some pulsed, some tonal, that combine into phrases, and the phrases combine into themes, and the themes are repeated in a specific order for the full length of the song. And when the whale finishes singing the song, it starts again, from the beginning, and repeats the same sequence for hours or even days, without significant variation. This is not a random collection of noises. It is a deliberately constructed acoustic composition produced almost exclusively by males during the breeding season, and it is believed to serve a role in mate attraction and social display. Different populations of humpback whales have different songs. The humpbacks in the North Pacific sing a different song than the humpbacks in the North Atlantic. And the humpbacks in the Southern Hemisphere sing different songs again, but within a single population, all the males sing essentially the same song. They do not inherit this song genetically. They learn it from each other by listening. And over time, the song changes. Small variations appear, catch on, spread through the population, and over the course of a few years, the song evolves into something measurably different from what it was before. This has been documented in careful detail off the coast of Australia. In the late 1990s, a small group of humpback whales from the population that breeds off Western Australia apparently heard the song being sung by humpbacks from an entirely different population, the one that breeds off the eastern coast of Australia. The songs were distinct. The eastern population sang one song, the western population sang another, but somehow, probably during feeding migrations in the Southern Ocean, a small number of western whales picked up the Eastern song. When they returned to their own breeding grounds, they began singing the Eastern song. And within 2 years, nearly the entire Western population had switched. They abandoned the song they had been singing for years and adopted the new one, wholesale. It was the acoustic equivalent of an entire country abandoning its language and adopting a new one in the course of a single generation, because a handful of travelers had come back with something different and better. No one fully understands why this happens. Scientists have theories about novelty attraction, about sexual selection, about the social dynamics of acoustic learning in long-lived animals, but the underlying mechanism remains mysterious. But here's what most people never realize about humpback song. It is not a fixed trait, not a species-level instinct, but a culturally transmitted artifact. Something that is learned, varied, transmitted, and evolved over time within a population. The humpbacks are doing something that looks remarkably like what humans do with music and language. They are making art. They are creating shared cultural traditions. They are passing those traditions from individual to individual and from generation to generation. And they are doing it all in a medium, the deep ocean, where we can only barely observe them. Take a moment to sit with this, because it is one of the strangest things about the acoustic ocean. For them, songs are not ornamental. For them, songs are social. For them, songs are one of the primary ways that one whale connects with another. And those connections stretch across distances that, on land, would be impossible to bridge. A single humpback singing off the coast of Hawaii can potentially be heard by other humpbacks at distances of tens or even hundreds of kilometers, depending on the conditions. And because all the humpbacks in the North Pacific are singing the same song at the same time during the breeding season, the entire breeding ground becomes a kind of vast acoustic chorus, with hundreds or thousands of male whales all broadcasting the same complex composition into the water around them. The sound does not just fill the space, it defines the space. It is the primary sensory reality of every humpback in the area. They are not just hearing each other, they are inside each other's songs. And still, we have not touched the strangest end of the acoustic spectrum. Because beyond the low-frequency calls of the baleen whales, the blue whales, the fin whales, the humpbacks, there exists another group of whales whose acoustic lives are oriented in a completely different direction. Not toward long-distance communication at low frequencies, but toward active sensing at extremely high frequencies. The echolocators. The toothed whales. The sperm whale is the largest of the toothed whales, reaching about 18 meters in length and weighing up to 40 tons, and it produces one of the most powerful sounds of any living organism. A sperm whale's click can reach a peak sound pressure level of about 230 decibels, which is substantially louder than even the blue whale's call. Sperm whale clicks are short, just a few milliseconds in duration, but they are so intense that at close range the acoustic energy could theoretically stun or disorient smaller animals, and has been proposed by some researchers as a hunting mechanism. But the primary function of the clicks is echolocation. The sperm whale produces a directional pulse of sound, aimed forward through a specialized organ in its enormous head, and listens for the echo of that pulse bouncing back from objects in the water ahead. By analyzing the timing, amplitude, and pattern of the returning echoes, the whale can build up a detailed acoustic picture of its surroundings. The location of prey, the shape of the seafloor, the presence of other whales, the boundaries of underwater features, all in complete darkness. At depths of up to 2,000 meters or more, where sunlight has not reached for the entire age of the species. The sperm whale's head is an acoustic instrument unlike anything else in the animal kingdom. The front third of the whale's body is occupied by two enormous oil-filled structures. the spermaceti organ, and the junk, that together act as a kind of biological amplifier and focusing system. When the whale produces a click, the sound is generated near the front of its head by a structure called the phonic lips, passes backward through the spermaceti organ, reflects off a cartilaginous surface near the skull, and then passes forward through the junk, emerging from the front of the head as a focused, intensely directional beam of sound. The anatomy is so precisely tuned that every individual sperm whale carries, in the shape of its own head, a specialized sonar apparatus that evolved over millions of years, specifically for the purpose of hunting in the deep ocean. And they do hunt in the deep. Sperm whales dive deeper than almost any other air-breathing animal on Earth, descending regularly to depths of 1,000 meters or more, and sometimes to more than 2,000 meters, in search of their favorite prey, the deep-sea squid, including the giant squid and the even larger colossal squid. At those depths, there is no light. There is no visibility. The squid that the sperm whales hunt are silent and nearly invisible, drifting through the black water. Without echolocation, finding them would be impossible. But with the powerful, directional clicks of the sperm whale's acoustic system, the whale can scan the water ahead of it with extraordinary precision, picking up the shape and motion of a squid from tens of meters away, closing in and striking in total darkness. Think of what this means as a way of being in the world. A sperm whale at a depth of 1,000 meters, in water so dark that even its own eyes can contribute almost nothing to its perception of the environment, is not experiencing darkness in the way we would experience it. It is experiencing a richly detailed acoustic landscape. Each click it produces returns an echo that outlines the objects in front of it, the seafloor rising and falling, the other whales in its pod, the moving shapes of squid, the occasional hard surface of a shipwreck or a rocky outcrop. The sperm whale is essentially seeing in sound. And because sound in water travels much faster and reaches much further than light in any terrestrial environment, the sperm whale's acoustic vision is in some ways more powerful than the visual sense of any land animal. It can scan volumes of ocean at distances that would be unreachable to the eye. It can perceive the shape and motion of prey through walls of dark water. It can, in effect, see the invisible. And this is not the only echolocating species. Every toothed whale, the orcas, the dolphins, the beaked whales, the pilot whales, the narwhals, the belugas, uses echolocation in some form. Some of them, like the dolphins, produce extremely high-frequency clicks that can resolve details on the scale of centimeters, allowing them to distinguish between different species of fish at a distance, or to detect small objects buried in sand. Some of them, like the beaked whales, produce clicks only at specific depths during specific phases of a dive, using echolocation for brief, intense foraging bouts deep in the water column. Every species has its own acoustic profile, its own click patterns, its own way of sensing the dark ocean around it. And every species has evolved those patterns over millions of years of adaptation to the specific properties of underwater sound. For them, this environment is not extreme. For them, this is home. And the world above, the warm, bright, low-pressure world where we live, where sound fades within meters, and most communication happens through the air, would be as limited to them as the deep ocean is to us. A sperm whale trying to hunt in a forest would be helpless. Its acoustic system, so extraordinary in the water, would be useless in a medium where sound barely travels, where distant objects do not produce clear echoes, where the air itself absorbs and scatters the frequencies that the whale depends on. For a creature adapted to the acoustic ocean, The world of air is silent in a way that ours is not. It is a world where the rich, continuous soundscape of the sea has been replaced by a thin, fragmented, quickly fading stream of local noises. A world where the basic sense of where you are and what is happening around you would be almost completely absent. But we are still not deep enough into the acoustic world of the sea, because so far we have talked only about the voices of large animals, the whales whose calls and songs and clicks dominate our popular image of underwater sound. But the ocean is filled with other sounds. Sounds produced by animals most people have never heard of, sounds that form the background texture of the underwater world, sounds that go on constantly day and night for the entire history of the ecosystem in which they occur. And one of the most surprising of these, one that demonstrates just how acoustically alive the ocean really is, comes from an animal so small, so unassuming, that you have probably never given it a second thought. Let's talk about the pistol shrimp. The pistol shrimp is a small crustacean, usually about 5 centimeters long, that lives on the floors of coral reefs and other warm, shallow ocean environments around the world. It looks unremarkable. A small, vaguely lobster-shaped animal with one claw dramatically larger than the other, scuttling about in the crevices of the reef. You could walk past dozens of them in a tidal pool and never notice that anything unusual was happening. And yet the pistol shrimp, for its size, may be the loudest animal on Earth. The trick is in its oversized claw. When the pistol shrimp wants to stun prey, or to fight off a rival, or simply to warn another shrimp to stay out of its territory, it snaps that claw shut with extraordinary speed. The claw has a specialized mechanism, a latch and spring system built into the joint, that allows it to close faster than a shrimp's muscles alone could close any ordinary claw. The snap is so rapid and so violent that it sends a jet of water shooting out of the claw at speeds approaching 100 kilometers per hour. And that jet of water moves so fast that it causes cavitation, the formation of a small vapor bubble in the water caused by the pressure dropping below the vapor pressure of seawater in the wake of the shrimp's claw. For a few microseconds, a bubble exists where a moment before there was only liquid, and then the bubble collapses. When the cavitation bubble collapses, it releases a burst of energy so intense that the temperature inside the imploding bubble reaches thousands of degrees. Some estimates suggest it briefly approaches the surface temperature of the sun. It also produces a loud, sharp, explosive sound. Measured close to the shrimp, the snap of a pistol shrimp's claw can exceed 200 decibels, which makes it acoustically louder than a rifle shot, louder than most explosions, and comparable to the sound pressure levels produced by the largest man-made underwater weapons. The prey in front of the shrimp, if it is a small fish or another crustacean, is often killed instantly, not by the claw itself, which never quite closes on the prey, but by the shockwave of the collapsing cavitation bubble, which is powerful enough to stun or kill at close range. But here's what most people don't realize. The pistol shrimp is not a rare animal. It is extraordinarily common, particularly in tropical coral reef environments, where hundreds of them can live in a single square meter of reef. And every one of them is snapping its claw over and over again throughout the day and night as part of its normal life. The result is that the soundscape of a tropical coral reef is not the quiet, peaceful, blue-green world of nature documentaries. It is a crackling, continuous percussive roar, a constant, staticky symphony of tens of thousands of small explosions per minute produced by the pistol shrimp populations, covering the reef, going on indefinitely, for as long as the reef itself exists. Hydrophones placed near a healthy coral reef pick up a sound that, to human ears, sounds like the continuous frying of bacon in a pan, or the crackling of a vast, distant campfire. It is the sound of 1 million small animals, each producing a sound pressure comparable to a rifle shot, all of them snapping independently, all the time. This is the true acoustic reality of a coral reef. What looks, from above, like a quiet underwater garden, is in fact one of the loudest places in the ocean. And the fact that most people have never heard this, that the popular image of the reef is one of gentle tropical calm rather than violent acoustic chaos, is a reminder of how much of the ocean's real character exists outside of what our senses, designed for life on land, are capable of perceiving. The reef is not silent. The reef is never silent. It is acoustically one of the most active environments on the planet, sustained by the continuous cavitation of shrimp claws and the calls of thousands of fish and the scraping of invertebrates across coral surfaces, in a soundscape that has been going on more or less uninterrupted for as long as coral reefs have existed on Earth, and the fish add their own layers to this soundscape. Many species of reef fish produce deliberate sounds, and they do so for the same reasons that land animals vocalize: to attract mates, to defend territory, to communicate with their offspring, to signal distress. Groupers produce deep, booming sounds by contracting muscles against their swim bladders, using the bladder as a resonant drum. Damselfish chirp and pop. Toadfish hum at frequencies that can be felt through the hulls of boats above them. Croakers, as their name suggests, croak, and during certain times of the year in certain places, entire populations of fish gather together to spawn, and their combined vocalizations produce what scientists call fish choruses, periods of intense, coordinated sound production that can dominate the acoustic environment of a reef for hours at a time at volumes loud enough to interfere with naval sonar operations. During the spawning season in the Gulf of Mexico, the black drumfish, a large Atlantic species that can grow to over 1 meter in length, forms massive aggregations of thousands of individuals, and they produce a collective sound so loud and so persistent that residents of coastal communities in Florida have occasionally complained about low-frequency humming noises coming from the water at night. The humming is real. It is the combined voices of tens of thousands of drumfish contracting their swim bladders in unison, producing a bass rumble that carries kilometers through the water and into the air above, reaching the houses on the shore. The fish do not know that humans can hear them. They are simply doing what they have always done, producing the sounds that allow them to find each other in the vast, dark waters of the Gulf. And the humans on land, lying awake at night, become accidental listeners to an acoustic event that has been going on in the same waters since long before any human city existed on that shore. Think about what this means. The ocean is not a quiet place that occasionally contains sounds. The ocean is a place where sound is the default. Every depth, every environment, every ecosystem is producing its own continuous acoustic signal, made up of the overlapping voices and movements of countless organisms, each one contributing to a complex, layered, ever-changing soundscape. And most of these sounds, most of the time, are not heard by any human. They exist, they are produced, they carry meaning between the creatures that produce them, and they fade back into the ambient noise of the sea without ever crossing the threshold of our awareness. We live next to this vast acoustic world, and we spend our lives largely oblivious to it. But the sounds do not stop with the living creatures. The ocean itself, as a physical system, produces sound. And some of those sounds are among the strangest acoustic phenomena anywhere on Earth. Consider the icequakes. Icequakes, technically called cryoseisms, are the sounds produced when large masses of ice crack, fracture, or collide with each other. They occur most frequently in the Antarctic and Arctic. where glaciers carve enormous icebergs into the surrounding ocean, and where existing icebergs sometimes collide with the seafloor or with other icebergs during their slow drift across the polar seas. The sounds produced by these events can be enormous. A single large iceberg cracking along its length as it breaks away from a glacier produces a burst of low-frequency acoustic energy that can propagate for thousands of kilometers through the ocean, reaching hydrophones on the other side of the planet. The icequakes of Antarctica are, in some ways, the largest non-biological sounds in the modern ocean, and they happen constantly. Hydrophones deployed in the Southern Ocean pick up tens of thousands of icequake events per year as the ice shelves and iceberg populations of Antarctica continue their slow, endless process of cracking, carving, grinding, and disintegration. In 1997, the United States National Oceanic and Atmospheric Administration, usually known as NOAA, was monitoring the equatorial Pacific with an array of autonomous hydrophones that had been set up, in part to track seafloor volcanic activity. One day, the hydrophones picked up a sound so loud, so unusual, and so striking that it stood out immediately from all the other acoustic data the array had been collecting. The sound was an ultra-low frequency, rising and falling tone that lasted for about a minute. It was detected by hydrophones more than 3.000 kilometers apart. It did not match the acoustic signature of any known whale species. It did not match any known geological process, and it was loud enough at that distance to suggest a source of enormous acoustic power. Scientists at NOAA nicknamed the sound the bloop. For years after its detection, no one could say with certainty what the bloop was. The fact that it was louder than any known whale call, but had a somewhat organic, varying quality gave rise to speculation that it might have been produced by some enormous undiscovered creature, an unknown species of whale, perhaps far larger than any previously documented. Popular articles and online discussions spun increasingly elaborate theories. The ocean was vast, they pointed out, and we had mapped so little of it. Why should there not be something down there, some enormous creature we had never seen, that could produce a sound loud enough to be detected across an entire ocean basin? The bloop became, for a time, a kind of modern sea monster, a mystery sound from the depths, possibly biological, possibly something so strange that it defied explanation. But by around 2012, after more than a decade of additional acoustic monitoring in the Southern Ocean, NOAA scientists arrived at a different conclusion. The bloop was not a creature. It was an icequake, a large iceberg, cracking and breaking somewhere in the Antarctic, probably near the Bransfield Strait or the Ross Sea, had produced a burst of low-frequency sound that propagated thousands of kilometers north into the equatorial Pacific, where the hydrophones recorded it. The acoustic signature of the bloop matched, in every important detail, the signatures of other icequakes that NOAA had since recorded in the Southern Ocean. The mystery was solved. The sea monster turned out to be ice, and yet the existence of the bloop and the length of time it took to explain illustrates something important about the acoustic ocean. The fact that we could seriously consider, for years, that an enormous unknown creature might have produced the sound tells you something about how much we still don't know. We had not ruled out the possibility. We had simply not found an alternative explanation. The ocean is large enough, and our knowledge of it is sparse enough, that enormous creatures producing enormous sounds are not automatically excluded from the realm of possibility. And even today, as the hydrophones continue to record, new sounds appear in the data that we have not yet explained. Some of them, probably, are the voices of species we have not yet discovered. Some of them, probably, are geological processes we have not yet characterized, and some of them may remain unexplained for years or decades, sitting in the archives of acoustic data, waiting for someone to connect them to their source. And still, we have not reached the strangest acoustic event in the ocean. Let me tell you about a whale that no human has ever seen. In 1989, researchers at a United States Naval Air Station on Whidbey Island, in the Pacific Northwest, were analyzing recordings from the SOSUS hydrophone array, the classified network of underwater microphones that the Navy had deployed during the Cold War to track Soviet submarines. Most of what they heard was ordinary. There were whale calls, of course. There was the sound of ships moving through the water. There were the deep rumbles of distant earthquakes. But one day, they picked up something that did not fit any category. It was a whale call, clearly biological, clearly produced by a single individual, but it was at a frequency of 52 Hz, which was much higher than the usual frequencies of the great whales. Blue whales call at 10 to 25 Hz. Fin whales call at 20 Hz. This new call was more than double the frequency of either, and it did not match any known species. The naval analysts listened to the recording for a while, noted it as an anomaly, and moved on. It was not until several years later, when some of the data from the SOSUS array was declassified and shared with civilian scientists, that the 52 Hz call was brought to the attention of a marine biologist named William Watkins at the Woods Hole Oceanographic Institution. Watkins began tracking the call, and what he found was remarkable. The 52 Hz call was being produced continuously. Year after year, season after season, the same distinctive signal was appearing in the hydrophone data. It was migrating in patterns that roughly resembled the migration patterns of blue whales or fin whales. It was traveling across the North Pacific, from the Aleutian Islands in the north to the waters off California in the south. And it was, as far as anyone could tell, being produced by a single individual. One whale, alone, somewhere in the Pacific Ocean, calling at a frequency that no other known whale produces. Scientists have tracked the 52 Hz whale for more than 3 decades now. It was tracked by Watkins until his death in 2004, and has been tracked intermittently by other researchers since. Its call has, over the years, drifted slightly downward in frequency, from 52 Hz in the late 1980s to around 49 Hz by the 2010s, which is consistent with what scientists would expect for an individual whale aging and maturing over time. And in all the years of tracking, through hundreds of thousands of hours of recorded data, no other whale has ever been recorded responding to the 52 Hz call. No other whale produces a call at that frequency. No other whale travels on that pattern. The 52 Hz whale appears to be, in every measurable sense, alone. It became known, in popular culture, as the loneliest whale in the world. Scientists are cautious about the anthropomorphism involved in calling any animal lonely. Whales have rich social lives that we do not fully understand, and the 52 Hz whale may well encounter and interact with other whales in ways that do not show up in acoustic recordings. One prominent theory is that the whale is a hybrid, a cross between a blue whale and a fin whale, two species that occasionally interbreed, and that its unusual call frequency is simply a biological consequence of its mixed genetic heritage. Other blue and fin whales may hear its call perfectly well and recognize it as a whale sound, even if they do not respond in kind. The whale may not be socially isolated, it may just be acoustically distinctive. And more recently, there have been detections suggesting that perhaps a second whale with a similar frequency signature exists meaning the 52 Hz whale may not be entirely unique after all. But the basic facts remain, and they are striking. Somewhere in the Pacific Ocean, for more than 30 years, a single whale has been producing a call at a frequency unlike that of any other individual we have ever recorded. It has been traveling thousands of kilometers a year. It has been broadcasting its presence into the acoustic void. And we have been listening from a great distance, through a network of hydrophones that were originally built for military purposes, recording the voice of a creature we have never seen and probably never will see. Think about what this means as a way of being. Somewhere, right now, that whale is probably calling. In water so deep and so dark that vision would be useless in currents that have been moving for thousands of years. Surrounded by the sounds of other whales, producing calls at other frequencies, the 52 Hz whale continues to sing its distinctive, slightly out-of-place song in a frequency that no other whale quite matches. It has been doing this for longer than some of the scientists studying it have been alive. And it will probably continue, assuming it lives a normal bluefin hybrid lifespan, for decades more. A single individual, producing a single recurring signal, moving slowly through the North Pacific, calling into the darkness, receiving no answer that we can detect, and yet continuing year after year, as though the calling itself were what mattered. The ocean is large enough to hold that kind of solitude, and acoustic enough to let us hear it from thousands of kilometers away through the medium of the sea. And still, we have not finished describing the acoustic ocean. Because so far, we have talked about the biological sounds, the whales, the shrimp, the fish, and the geological sounds, the icequakes, and the seafloor volcanoes, and the distant earthquakes. But there are other kinds of sounds that come from nowhere, in particular sounds that belong to the ocean as a whole. Sounds that are produced not by any single organism or event, but by the constant motion of the entire system. The ambient noise of the ocean is itself a kind of acoustic signature. At any given moment, anywhere in the deep sea there is a continuous low-level sound coming from no obvious source. A diffuse, ever-present background of noise that persists at every depth and in every ocean basin. Scientists have a name for this. They call it the deep ocean ambient noise spectrum, and it is one of the most carefully measured properties of the marine environment. Below about 10 Hz, most of the ambient noise is caused by large-scale ocean motion. Distant storms, the movement of major currents, the slow flexing of the seafloor under the weight of the water above it. Between 10 and a few hundred Hz, the dominant source of ambient noise is distant shipping. Above that, the dominant source is wind and wave action at the surface, where breaking waves entrain bubbles of air into the upper layers of the ocean, and those bubbles oscillate and collapse and produce continuous hissing noise that permeates the water column for hundreds of meters below. There is also the sound of rain. When it rains on the surface of the ocean, each raindrop impacts the water and produces a small, distinctive acoustic pulse. Multiplied by the hundreds of thousands or millions of raindrops falling on a square kilometer of ocean during a storm, the cumulative sound of rain becomes a significant contributor to the underwater soundscape. Scientists can actually measure rainfall over open ocean by listening for its acoustic signature with underwater microphones. A large storm system passing over a region of the Pacific produces a characteristic acoustic fingerprint that can be picked up hundreds of kilometers away, giving hydrophone networks a kind of rough weather monitoring capability. You can hear, from the deep sea, whether it is raining at the surface. And there are the sounds of the seafloor itself. The Earth's crust, beneath the ocean, is not a static surface. It is constantly shifting, not dramatically, not in ways that would be obvious to a casual observer, but at the microscale, in countless small adjustments, as plates grind past each other, and as the immense weight of water pressing down on the crust causes tiny ongoing deformations. These produce a continuous low-frequency rumble that hydrophones detect as a kind of planetary bass note, always present, always varying slightly, never completely absent. The Earth, listened to through the ocean, is never fully quiet. There is always something happening somewhere. A small earthquake on a distant fault, a submarine volcano venting gases, a landslide on the continental slope. And all of those events produce acoustic signals that propagate through the water column and add their voices to the ongoing ambient noise. One particular kind of seafloor sound deserves special attention. When an earthquake occurs underwater, the seismic energy released by the quake can couple into the ocean water and produce acoustic waves that travel through the SOFAR channel at the speed of sound in water rather than at the speed of seismic waves in rock. These waterborne acoustic signals are called T-waves or tertiary waves, and they have a distinctive signature. They arrive after the primary and secondary seismic waves. They travel more slowly, and they can be detected at enormous distances by underwater hydrophones. T-waves are one of the primary tools that seismologists now use to characterize small underwater earthquakes, because they often propagate with less attenuation than seismic waves traveling through the crust, and because the global hydrophone network can detect them even from remote parts of the ocean, where there are no nearby seismic stations. In 1991, after the decline of the Soviet Union reduced the military need for some of the American hydrophone networks, the US Navy gradually began to declassify portions of its acoustic data and to allow civilian scientists access to the SOSUS system. The name SOSUS stands for Sound Surveillance System, and it was one of the largest scientific infrastructure projects of the 20th century. A global network of underwater hydrophones laid on the seafloor along strategic points in the North Atlantic and North Pacific, specifically designed to detect the acoustic signatures of Soviet submarines at long range. The system had been enormously successful, and for decades it had allowed the United States to track Soviet submarine movements with a precision that the Soviets themselves did not fully understand. SOSUS could detect a single submarine from more than 1,000 kilometers away, identify its class by the sound of its engines, and monitor its course across entire ocean basins. And when portions of that network became available to civilian researchers, a revolution began in marine acoustics. Scientists at the Pacific Marine Environmental Laboratory, a NOAA facility, were among the first to gain access. They began listening to the ocean with equipment that had never been available to civilian science before, and what they found was astonishing. They could hear small earthquakes that had never been recorded by any land-based seismic station. They could detect submarine volcanic eruptions as they happened, and track the resulting acoustic plumes across thousands of kilometers. They could follow the migrations of individual whale populations. They could pick up the signatures of ice-carving events in Antarctica. They could, in short, listen to the entire ocean at a level of detail that had previously been the exclusive domain of the military, and they could go back through the archives. The SOSUS system had been in operation in various forms since the 1950s. That meant there were decades of recorded acoustic data, entire oceans of sound, catalogued by military listeners for military purposes, sitting in archives where it had never been analyzed for scientific content. When civilian scientists began to sift through this data, they found, among many other things, the first recorded instances of the 52 Hz whale, going back to the late 1980s. They found patterns of whale migration across multiple decades, They found changes in ambient noise levels that correlated with the rise of global shipping. They found a planet full of acoustic information that had been, until then, hidden behind classification. The revelation was that the ocean had been singing this whole time, in a language that had been recorded but not translated, and now that the recordings were available, a whole new branch of science opened up. Marine bioacoustics, the study of sound in the sea, produced by both biological and non-biological sources, became a major research field almost overnight. Universities set up dedicated programs. Conferences were held. Papers were published by the thousands. The ocean, which had been treated for so long as a visual place to be explored with cameras and submersibles, was now understood to be perhaps, primarily, an acoustic place that could be explored just as rigorously with microphones. And in this new age of marine acoustics, a number of mysteries began to accumulate. The bloop was one of them, eventually solved. The 52 Hz whale was another, still unresolved in its essentials. There are others. There is a sound called Julia, recorded in 1999, which also appears to have been caused by ice carving, but whose exact origin has never been definitively pinpointed. There is a sound called the upsweep, which has been recorded since 1991, and which appears to be linked to underwater volcanic activity, but which has some strange properties that do not quite fit the volcanic hypothesis. There is a sound called the slowdown, which was recorded once in 1997 and then never again, and which remains unexplained. The deep archives of acoustic data are full of these anomalies, brief, unusual, sometimes dramatic sounds that do not match any known source, some of them recorded by hydrophones listening in ocean basins where no human had ever been, some of them lasting only seconds, some of them fading into silence, never to recur. Each of these mysteries reminds us of the essential point. The ocean is full of sound. Most of that sound is produced by processes we understand. Whales, fish, ice, earthquakes, ships, weather. But a non-trivial fraction of it, particularly in the deep archives of long-term acoustic monitoring, is produced by things we do not yet understand. Undiscovered species. Unknown geological processes. Events whose acoustic signatures are all we have, because the events themselves happen too fast, or too deep, or too far away for any other form of observation to catch them. The acoustic ocean, like the physical ocean, is still largely unmapped, and every year of listening adds new entries to the catalogue of what we can hear but cannot yet explain. But we are still not done with the history of how humans learned to listen to the sea. Let's go back further to the very beginnings of underwater acoustics, because the story of how humans first came to understand that sound travels through water is older and stranger than you might expect. The first known experiment in underwater sound was conducted in 1490 by Leonardo da Vinci, who wrote in one of his notebooks that if you sink a long tube into the water and put your ear to the upper end, you can hear ships at great distances. Da Vinci did not publish this observation in any formal scientific sense, and it attracted little attention at the time. But it was the first recorded demonstration that the ocean carries sound in a way that the air does not. The tube was acting as a kind of primitive hydrophone, a way of coupling the human ear to the underwater acoustic field, bypassing the impedance mismatch between water and air that normally makes it hard for us to hear underwater sounds from the surface. For the next 3 centuries, underwater acoustics remained essentially a curiosity. A few experiments were performed. In 1826, a Swiss physicist named Jean-Daniel Colladon, working with a French mathematician named Charles-François Sturm, made the first accurate measurement of the speed of sound in water. They did this on Lake Geneva, in Switzerland. One boat carried a bell submerged in the water and a signal fire. A second boat, stationed some distance away, had an observer who watched for the flash of the fire and listened, with an underwater horn, for the sound of the bell. By measuring the time delay between the flash and the sound, and knowing the distance between the boats, they calculated the speed of sound in fresh water to be approximately 1.435 meters per second, a value that turned out to be remarkably close to the modern accepted figure of about 1.480 meters per second in fresh water, or about 1.500 meters per second in seawater. This was the first reliable measurement of how fast sound travels through water, and it established that water is indeed a much faster medium for sound than air. But the real birth of underwater acoustics as a serious scientific field came in the early 20th century, driven like so many advances in technology by the imperatives of war. During the First World War, the military problem of detecting submarines underwater became urgent because German U-boats were sinking Allied shipping in the North Atlantic at a catastrophic rate. Scientists and engineers on both sides of the conflict began developing underwater listening devices, early hydrophones, essentially underwater microphones that could detect the sounds of submarine engines and propellers. By the end of the war, these devices had been deployed on warships and on fixed listening stations, and they had significantly reduced the threat of submarine attack. More importantly, they had established that underwater listening was a viable military technology, and that the ocean contained acoustic information that could be decoded to reveal the location and behavior of vessels moving through it. The Second World War accelerated this work enormously. By the early 1940s, the Allied powers were investing heavily in both active sonar, which sends out a pulse of sound and listens for echoes, the underwater equivalent of radar, and passive listening systems which simply record the acoustic signals already present in the water. It was during this period that Maurice Ewing and his collaborators at Columbia University made the crucial theoretical and experimental breakthroughs that led to the discovery of the SOFAR channel. Ewing had a specific practical motivation. He wanted to develop a system by which downed pilots floating in life rafts in the open ocean could signal their position to rescue forces. The idea was that a pilot could drop a small, specially designed explosive charge, a SOFAR bomb, into the water where it would sink to the depth of the sound channel and detonate. The resulting acoustic pulse would propagate through the SOFAR channel to hydrophones thousands of kilometers away. By measuring the arrival time at multiple stations, rescuers could triangulate the position of the pilot and send help. The system worked. SOFAR bombs were deployed during the Second World War, and there are documented cases of pilots being rescued because of them. More importantly, the experiments that Ewing conducted to develop the system also confirmed in detail the acoustic properties of the deep sound channel. They showed that low-frequency sound, emitted at the right depth, could propagate for thousands of kilometers with very little loss of energy. They showed that the sound channel existed in every major ocean basin, at slightly different depths depending on local temperature and salinity conditions. They showed that the ocean was, as a physical system, uniquely suited to the long-range propagation of acoustic signals. And after the war, this discovery was put to use on a much larger scale. The Cold War that followed created a new military need for detecting Soviet submarines, and the United States Navy began in the late 1940s and early 1950s to build a permanent network of hydrophones along the seafloor of the Atlantic and Pacific Oceans. This was the beginning of SOSAs. By the early 1960s, the network included hundreds of individual hydrophones. strategically placed at depths corresponding to the SOFAR channel and connected by long submerged cables to shore-based listening stations. The system was enormously expensive and elaborately secret. The fact that the American submarine tracking capability was based on the SOFAR channel and that the Soviets could not easily detect or disrupt the system remained a closely guarded strategic advantage for decades. What the Navy heard through SOSAs during all those years was a mixture of the signals they were looking for and many signals they were not looking for. Soviet submarines, yes. Surface ships, yes. But also whales. Millions of hours of whale song, recorded incidentally as the system listened for military targets, and earthquakes, and volcanic eruptions, and icequakes, and ship noise, and the ambient noise of the sea, and all the other acoustic events that happen to occur within range of the network. Almost all of this data was classified. Much of it was considered irrelevant to the military mission and simply discarded. But a significant portion was archived, and when the Cold War ended and access was opened to civilian scientists, those archives turned out to be one of the most valuable scientific resources ever assembled about the deep ocean. It is hard to overstate how much what we know about whales, in particular, comes directly from military hydrophone data. The patterns of blue whale migration in the North Pacific, the seasonal distribution of fin whale populations in the North Atlantic, the dialects of humpback whale songs across different populations. Many of the fundamental results of modern whale biology were extracted from recordings that had been made by the Navy for entirely different reasons. The whales had been singing into the ocean. The Navy had been listening for submarines. But the Navy's equipment had, incidentally, been recording the whales as well. And when scientists got access to the data, the whales were all there clear as day. Tens of thousands of hours of their calls going back, decades, a whole acoustic record of cetacean life preserved by accident in the archives of a military surveillance system. There is something strange and almost poignant about this. The songs of whales, some of the most ancient and most distinctive biological sounds on Earth, were preserved for the use of future scientists by the infrastructure of a superpower conflict. The whales did not know that they were being recorded. The Navy did not particularly care about the whales, but the recordings happened, and the recordings lasted, and now, decades later, those recordings are some of the most important primary data in marine biology. A byproduct of one kind of listening turned out to be central to another kind of listening. The ocean had been singing. Humans had been listening for their own reasons, and in the space between the singing and the listening, an accidental archive had accumulated, one that we are still learning how to read. In the decades since the end of the Cold War, marine acoustics has become one of the most active and most surprising fields in all of oceanography, and scientists have begun to use the acoustic properties of the ocean for purposes that the original military designers of SOSUS would scarcely have imagined. One of the most remarkable of these is the use of underwater sound to monitor the temperature of the deep ocean itself. The idea is elegant, and it follows directly from the physics we have already discussed. Because the speed of sound in seawater depends on temperature, faster in warmer water. Slower in cold, it is possible to measure the temperature of a large volume of ocean by measuring how long it takes for a sound to travel across that volume. If you send a known acoustic pulse from a source at one location, and you detect the arrival of that pulse at a receiver thousands of kilometers away, the exact time it took for the sound to travel from source to receiver tells you something about the average temperature of all the water in between. A slightly warmer ocean means a slightly faster arrival. A slightly colder ocean means a slightly slower arrival. By making repeated measurements over years and decades, you can track the thermal evolution of enormous volumes of the deep sea. This technique is called acoustic thermometry, and in the early 1990s, it was the basis of one of the most ambitious scientific projects ever attempted. It was called ATOC, which stood for Acoustic Thermometry of Ocean Climate, and it was led by a physicist named Walter Munk, working at Scripps Institution of Oceanography in California. Munk was one of the great figures of 20th century oceanography. He had worked on underwater sound since the Second World War, had collaborated with Ewing on SOFAR research, and had spent decades thinking about how acoustic methods could be applied to large-scale oceanography. By the late 1980s, he had become convinced that acoustic thermometry offered a unique opportunity to measure global ocean warming, a phenomenon that was only beginning to be recognized as a major scientific concern, with a precision that no other method could match. The initial concept was called the Heard Island Feasibility Test, after the remote subantarctic island where the acoustic source was placed, and it was conducted in January of 1991. A source was deployed at a depth of about 175 meters near Heard Island in the southern Indian Ocean, more than halfway between Africa and Antarctica, at one of the most remote points in the entire Pacific Indian Ocean system. The source emitted low-frequency acoustic signals and hydrophones positioned across the oceans. As far away as the coasts of North America and the North Atlantic listened for the arrivals. The results were astonishing. The signals from Heard Island were detected on every major ocean basin, on hydrophones more than 17.00 kilometers away. The sound had traveled through the SOFAR Channel, from the southern Indian Ocean across the Pacific and into the Atlantic, covering nearly half the circumference of the Earth, and it arrived at the distant hydrophones still recognizable, still measurable, still carrying useful information about the temperature of the water it had crossed. Think about that for a moment. A single acoustic signal, sent from a source in the middle of one ocean, was heard on the coast of another continent on the opposite side of the planet. Sound had traveled the width of a world. This was the SOFAR channel, working at its full capacity, the acoustic waveguide, operating as a true global network, carrying information across distances that in any other medium would be unthinkable. The Heard Island experiment confirmed that long-range ocean acoustic tomography was possible on a planetary scale. And it set the stage for a decade of experiments in which scientists attempted to use these techniques to measure ocean warming directly. The ATOC project itself was more controversial. It involved the deployment of acoustic sources off the coast of California and near Hawaii, which produced signals loud enough to be detected by hydrophones throughout the North Pacific. Environmental groups raised concerns about the effects of the sound on marine mammals, particularly the baleen whales, which communicate in the same low-frequency range as the ATOC signals, and a long and sometimes contentious debate followed about whether the scientific benefits of the experiment outweighed the potential harm to whale populations. Eventually, the project was modified and scaled back, but not before it had demonstrated across several years of measurements that acoustic thermometry could detect changes in deep ocean temperature with unprecedented precision. The results contributed to the broader scientific picture of climate change, and they established techniques that are still used in modified forms by oceanographers today. The debate over ATOC also illustrated something else, which is that the human use of the ocean for acoustic purposes, however scientifically valuable, has consequences for the creatures that live inside that acoustic environment. The whales that had been using the low-frequency channels of the ocean for their own communication for tens of millions of years were suddenly sharing those channels with man-made signals deliberately designed to be loud. long and easily detectable at great distances. The acoustic ecology of the ocean was being altered, and this, it has become increasingly clear, is not limited to scientific experiments. It is a general property of the modern ocean, a profound and mostly invisible form of pollution that has, in the course of a single human lifetime, transformed the underwater world in ways that we are only beginning to measure. Let's talk about what humanity has been doing to the soundscape of the sea. In 1940, the total amount of man-made sound in the world's oceans was, by modern standards, very small. There were naval vessels, there were fishing boats, there were the first scientific research ships. But the global fleet was tiny, the engines were small, and the dominant sound in the ocean was, as it had been for millions of years, the sound of biological and geological processes. Whales, shrimp, fish waves, rain. Earthquakes, ice. In the roughly 80 years since, this has changed drastically. The global commercial shipping fleet has grown by more than an order of magnitude. Cargo ships, oil tankers, container vessels, cruise liners, and military vessels now produce a continuous roar of low-frequency sound that covers most of the world's oceans day and night, every day of the year. The propellers of large ships generate cavitation, the same cavitation that pistol shrimp use to stun prey, but on a vastly larger scale. And the acoustic energy from this cavitation, combined with the rumble of engines and the sound of water rushing past hulls, produces a low-frequency noise floor that has roughly doubled in the North Pacific and North Atlantic every decade since the 1960s. This is not a minor change. The ambient noise in major shipping lanes, measured at the low frequencies used by blue whales and fin whales, is now estimated to be about 100 times higher than it was in the pre-industrial ocean. But here's what most people never consider about this change. The whales, whose calls evolved to propagate through a relatively quiet acoustic environment, now find themselves trying to communicate in an ocean that is filled with man-made noise in precisely the same frequencies that they use. The effective range of their calls has been dramatically reduced. Where a blue whale's call might once have been audible to other blue whales 1,000 kilometers away, in many parts of the modern ocean, that same call is drowned out by shipping noise within a few hundred kilometers. The acoustic world of the whales is shrinking, not because the whales have become quieter, but because the background against which they call has become louder. Scientists who have studied this change have documented behavioral responses in the whales. Blue whales have been observed calling more loudly in noisier environments, as though straining to be heard. Fin whales have shifted the frequencies of some of their calls slightly higher, apparently in an attempt to get above the lowest and loudest shipping noise. Humpback whales have altered the timing and structure of their songs in areas with heavy boat traffic, and some populations of whales have simply moved, abandoning traditional feeding or breeding grounds that have become too noisy for comfortable communication. The acoustic ocean, which has been the primary sensory environment of these animals for tens of millions of years, is being reshaped around them, and they are responding with the only tools available, changing their calls, changing their movements, changing their behavior, in an attempt to keep their acoustic world functional. But the changes are not only from shipping. There is also military sonar. Modern naval sonar systems produce pulses of sound at extreme intensities, specifically designed to travel long distances and return clear echoes from submerged objects. Some of these systems generate source levels above 230 decibels, which is louder than almost any biological sound in the ocean. The acoustic pulses can be heard by whales at distances of hundreds of kilometers. And there is now substantial evidence that military sonar, particularly the mid-frequency active sonar used for submarine detection, can cause direct harm to certain species of whales. Beaked whales. In particular, a family of deep-diving toothed whales that includes some of the most elusive cetaceans in the ocean have been documented stranding and dying in association with naval sonar exercises. The mechanism is not fully understood, but it appears that the intense acoustic stimulus disrupts the whale's diving behavior, causing them to surface too quickly, which leads to decompression injuries similar to those that affect human divers who come up too fast from deep dives. The result, in several documented incidents, has been mass strandings of dozens of beaked whales washing up dead on shorelines near where sonar exercises were being conducted. And then there is the acoustic impact of oil and gas exploration. The primary tool for finding subsea oil deposits is a technique called seismic airgun surveying, in which arrays of compressed air guns are towed behind ships and fired at regular intervals, typically every 10 or 15 seconds, continuously for weeks or months at a time, to send pulses of sound down into the seafloor. The echoes from deep rock layers are recorded and used to reconstruct the geology of the subsurface, helping oil companies identify potential drilling targets. The individual pulses from these airgun arrays can be heard thousands of kilometers away. In areas where seismic surveys are ongoing, the sound of airguns firing becomes a persistent, rhythmic thumping in the underwater soundscape, audible over enormous areas continuing for months. And the impact on marine animals, particularly the low-frequency communicators, is thought to be significant, though it is still being quantified. The cumulative effect of all this, shipping sonar seismic surveys, offshore construction, recreational boating research activities, is that the modern ocean is acoustically different from the ocean of even a century ago. It is louder. It is full of sounds that have no biological or natural origin. And those sounds occupy precisely the parts of the acoustic spectrum that marine animals depend on for their own communication and orientation. The acoustic habitat of the ocean is being altered in ways that are comparable in scale and in speed to the way that the visual habitat of land has been altered by the spread of artificial light. Just as nocturnal animals on land now live in a world where the night is never fully dark, many marine animals now live in a world where the ocean is never fully quiet in the way it used to be. The silences that their ancestors knew, the deep, uninterrupted acoustic stillness of the pre-industrial sea, are becoming increasingly rare. Take a moment to sit with this, because it is one of the most unnoticed environmental changes of our time. For the creatures of the acoustic ocean, the 20th and 21st centuries have been, in a very real sense, a sonic invasion. The ocean they inhabit has been overlaid with layers of industrial noise that never existed before. Their calls, which evolved over tens of millions of years to reach each other across vast distances, now have to compete with a continuous background that is far louder than anything they have ever encountered. And this change has happened, essentially, within the lifetime of individual whales. A blue whale born in the 1950s, which might still be alive today, has lived through the entire transformation of the ocean's soundscape, has heard the background noise rise decade by decade, has experienced the arrival of ship after ship after ship, has witnessed acoustically the industrialization of the sea. And still, even with all of this change, the acoustic ocean remains. The whales still call. The pistol shrimp still snap. The icebergs still crack. The earthquakes still rumble. The SOFAR channel still carries its signals across thousands of kilometers. The deep sound channel, laid down by the physics of temperature and pressure in the sea, has been there for as long as the modern ocean has existed, and it will be there for as long as the ocean itself lasts. We are adding to it. We are polluting it. We are making it harder for the other creatures to use, but we are not fundamentally changing what it is. The underlying acoustic structure of the sea is a property of the water and the thermal stratification, not a property of what lives in it. And below the industrial roar, the older voices continue, doing what they have always done, in the medium they have always used. For them, this environment is not new. For them, this is home. And the sounds they produce, however much they now have to compete with man-made noise, still serve their original purposes. The whale calls still carry. The echolocation clicks still find prey in the dark. The shrimp still stun their victims with cavitation. The fish still chorus in their seasonal gatherings. The ocean is still, at its fundamental level, an acoustic place, and the creatures that live in it are still, at their fundamental level, creatures of sound. What has changed is the background against which they operate, not the essence of what they are. And still, we have more to say about the acoustic ocean, because so far we have talked mostly about the big, loud, dramatic sounds, the whale calls, the ice events, the man-made noises. But the ocean is also full of quieter sounds, sounds at the edge of detection, sounds that take careful listening and sensitive equipment to hear. And some of these may be among the most important sounds in the sea. Let's talk about the sounds of the deep biosphere. The deep biosphere, as we have mentioned before, is the vast community of microbes that lives inside the sediments of the seafloor and the rocks beneath it. A living system that may represent the largest ecosystem on Earth by biomass, slowly metabolizing over timescales of centuries and millennia. These organisms do not produce sound in the way that whales or shrimp do. They are single-celled. They have no vocal apparatus. But they do produce sound in a subtle, almost undetectable way through the metabolic processes they carry out. When microbes in sediment break down organic matter, they produce gases: methane, hydrogen sulfide, carbon dioxide, and these gases sometimes accumulate in small bubbles that then rise through the sediment and release into the water above. Each such release produces a tiny acoustic event, a small pop or click as the bubble breaks through the sediment surface and enters the water column. Multiplied by the trillions of microbial processes happening constantly across the abyssal plain, these releases produce an almost imperceptibly soft, hissing, a background noise of deep sediment microbial metabolism, detectable only with the most sensitive equipment, but genuinely there, filling the acoustic space of the deep sea floor, with the cumulative whisper of the planet's oldest and slowest form of life. Similarly, the hydrothermal vents produce their own acoustic signatures. Water rushing out of a vent chimney at temperatures of 300 or 400 degrees Celsius produces turbulent noise, a hissing, roaring sound, like a continuous jet. The mineral particles precipitating out of the hot water as it meets the cold surrounding seawater make small acoustic events as they form. The shrimp and tube worms and other vent organisms move about, and their movements, too, produce sound. A vent field, listened to through a sensitive hydrophone, is not silent. It is a continuous, low-volume acoustic performance, the sound of chemistry and biology combining in one of the most unusual environments on the planet. And over all of this, over the biosphere sounds. Over the vent sounds, over the ambient noise of the deep. The long-distance voices of the whales continue to pass, traveling through the SOFAR channel, carrying their information across ocean basins, connecting individuals separated by thousands of kilometers in a slow, patient acoustic conversation. The ocean is, in every sense, a listening space. It is full of voices, and it has been, for as long as there has been life in the sea. And there is something else, something that deserves its own discussion, because it reveals the acoustic ocean at its most genuinely strange, its most unexpectedly sophisticated. The dolphins. Dolphins are small, intelligent toothed whales, members of the same general group that includes the sperm whales and the orcas and the beaked whales, and they occupy most of the ocean's warm and temperate waters. There are dozens of species, including the familiar bottlenose dolphin of coastal American waters, the spotted dolphins of the Atlantic, the spinner dolphins of the tropical Pacific, and many others. They travel in groups, often large groups, and they are among the most socially complex of all marine mammals. And they have developed a system of acoustic communication that is, in some respects, closer to human language than anything else ever documented in the animal kingdom. The key element of that system is something called the signature whistle. It was first described in the 1960s by a pair of American researchers named Melba and David Caldwell, who noticed that individual bottlenose dolphins, when isolated from their groups, produced a very specific, very consistent whistle that was unique to the individual. Each dolphin had its own whistle. The whistles differed from each other in their frequency modulation, the pattern of rising and falling tones, and within any given dolphin's repertoire, the signature whistle was stable, recognizable, and repeatable over years. The Caldwells hypothesized that these whistles functioned as a kind of acoustic name, an individual identifier that allowed dolphins to broadcast their identity to other members of their group. For several decades, this hypothesis remained contested. It was hard to prove that the signature whistle carried genuine identity information rather than simply reflecting the particular voice characteristics of the individual, the acoustic equivalent of different human voices producing the same word in slightly different ways. The question was finally resolved in 2006 by a team led by a Scottish biologist named Vincent Yannick, working at the University of St Andrews. Yannick and his colleagues designed an experiment in which they recorded the signature whistles of wild bottlenose dolphins in Sarasota Bay, Florida, a population that had been studied continuously for decades, with individual dolphins known by name to the researchers. Then they digitally manipulated the recordings to remove the specific voice characteristics of each caller, leaving only the frequency modulation pattern of the whistle. They played these synthesized, voice-stripped whistles back to the dolphins in the wild, through underwater speakers, and they watched how the animals responded. The dolphins responded to the calls of their relatives. The synthetic whistle of a dolphin's mother or sister, even with all of the original voice features stripped away, produced a measurable behavioral response. The dolphin would orient toward the sound, would approach the speaker, would vocalize in return. But when played the synthetic whistle of an unrelated dolphin, the same animals showed no particular interest. The result was clear. But here's what the experiment really demonstrated. The dolphins were not recognizing each other by voice. They were recognizing each other by the shape of the whistle itself, by the specific pattern of frequency modulation that defined each individual's signature. This was, effectively, a demonstration that dolphins have names. Not names in the full linguistic sense that humans have names, with all of the cultural machinery of naming conventions and social context. But names in the most functionally important sense, distinctive acoustic labels that identify specific individuals that are learned and used by conspecifics, that can be detached from the voice of the original caller and still carry identity information. When a dolphin produces its signature whistle, it is, essentially, calling out its own name. And when another dolphin responds, it is responding to the identity encoded in the shape of the call. This alone would be remarkable. But the system is more sophisticated than even this. Dolphins do not only use their own signature whistles. They also copy the signature whistles of other dolphins. When a mother dolphin is separated from her calf, she will sometimes produce the calf's signature whistle. Not her own. A kind of acoustic summoning, calling the calf by its name to bring it back. When two groups of dolphins meet in the open ocean, they exchange signature whistles in what appear to be mutual introductions. Each group learning the names of the individuals in the other. A bottlenose dolphin's repertoire in the wild includes not just its own signature whistle, but copies of the signatures of many other dolphins in its social network, used in specific social situations to address, summon, or refer to those other individuals. It is a system that bears striking similarities to the way humans use names in conversation, to call out to specific people, to refer to absent individuals, to identify one's self in social settings. Consider what this means. In the acoustic ocean across dolphin populations, spanning dozens of species there is a form of individual recognition that operates through learned, distinctive calls. Calls that function like names that are passed between individuals, like names that carry identity information, in a way that is independent of the particular voice of the caller. This is not something simple. This is not instinct. This is a cultural and cognitive system that developed over millions of years of evolution in the acoustic ocean, in response to the specific challenges of maintaining social bonds in an environment where visual contact is limited, but acoustic contact can reach across kilometers of water. The dolphins that live in Sarasota Bay today are the most thoroughly studied wild dolphin population in the world, and the recording archive of their signature whistles now spans decades. Individual dolphins have been tracked, acoustically and visually, across their entire lifespans. Their whistles have been documented from the first months of life, through the learning phase, when young dolphins experiment with different patterns, through the stabilization of the signature whistle, by about the end of the first year, and then across decades of stable use in adult life. A dolphin whose signature whistle was first recorded in the 1980s, and who is still alive today, is still using essentially the same call. Recognizable to the researchers who first described it, and to the other dolphins who have known that individual across its life. The signature whistle is an acoustic identity, and it persists. Take a moment to sit with what this implies. Somewhere out there, in the waters of Sarasota Bay, a dolphin is calling. The call is a specific pattern of rising and falling frequencies, lasting perhaps a second or two, repeated a few times in succession, and to every other dolphin within acoustic range, which, for a clear signature whistle in good conditions, can be several kilometers. That call carries information. It says, "This is me, this particular individual, known to you, known to the group, known in this community of dolphins that stretches across generations." The call means, "I am here. I am calling. Answer, if you want to find me." And other dolphins hearing the call may recognize the individual, may remember past interactions, may adjust their behavior based on who is calling and what relationship they have with the caller. The acoustic ocean in these coastal waters is not just full of anonymous sound. It is full of specific identities, calling and responding, maintaining a web of social relationships that extends across the lifespans of individuals and the generations of a population. And this is only one species. The orcas, or killer whales, which are really a kind of very large dolphin, have their own system of distinctive acoustic signals, not signature whistles exactly, but shared family-specific calls that identify the pod, the matrilineal group, the community to which an individual belongs. Different orca pods have different dialects. Calves learn the dialect of their mother and inherit it for life. Orcas from different dialect groups can hear each other, but they do not typically interbreed or associate closely, and the acoustic differences reinforce the social boundaries between populations. There are orca communities off the coast of British Columbia and Washington State that have been speaking in acoustic terms slightly different languages from each other for tens or hundreds of generations. And the languages are stable enough that they can be used by scientists to identify by sound alone which community a given individual belongs to. This too is culture. This too is acoustic identity passed down across time. Learned from one generation to the next, preserved in the calls of specific individuals, and in the shared repertoires of specific groups. The ocean is not just a physical medium for sound. It is, through the creatures that have evolved in it, a medium for social identity, for cultural transmission, for the persistence of specific acoustic traditions over thousands of years. The deep sound channel carries not only the raw acoustic energy of whale calls, but also the specific identities encoded in those calls. The individual dolphins, the matrilineal pods, the cultural lineages that have been passing their signature sounds down through the water for as long as these species have existed. For them, this is not just communication. For them, this is the fabric of social life. And it happens, all of it, in a medium that we on land can barely access, through senses that we do not share in an acoustic world that we are only beginning to understand how to listen to properly. Let's return now to the creatures that live in this acoustic world, and try, once more, to imagine what their experience must be like. Because for all of the physical description we have done, the SOFAR channel, the speed of sound, the decibels and the frequencies, the most important thing about underwater sound is not the physics. It is the perceptual world that the physics makes possible. The fact that sound travels 1,000 times further through water than through air is not, in the end, a property of the ocean alone. It is a property of the lives that have been lived inside that ocean. The whales and the dolphins and the shrimp and the fish have all evolved their senses and their behaviors around the particular way that sound works in water. Their experience of the world is shaped, at the deepest level, by the acoustic properties of the sea. Try to imagine being a blue whale. You are enormous, the largest animal that has ever existed, and you spend most of your life in the open ocean, moving slowly through water at a depth of a few hundred meters. The visual range of your eyes is only a few meters at most. Beyond that distance, the water fades to a uniform blue-black, and individual objects disappear into haze. But your ears, which are small openings on the sides of your head, embedded in the flesh of your skull, connected through bone conduction to the inner ear mechanisms, are tuned to frequencies far below the range of human hearing, and they pick up signals from extraordinary distances. You can hear other blue whales, sometimes 1,000 kilometers away. You can hear the low rumble of distant storms, the creaking of icebergs in the polar seas, the long deep moans of fin whales passing through the same frequency channel that your species uses. You can hear the background noise of the ocean itself, the sound of the whole world vibrating softly at the lowest frequencies. And you produce sound. Your calls, long, slow, structured pulses, emerge from your body through mechanisms that scientists are only beginning to understand, but they propagate outward into the water in all directions, traveling forward and sideways and down, entering the SOFAR channel and following its acoustic pathways across the sea. Other whales hear you. Other whales, somewhere, far away, hear the calls you make and know that you exist, and know, roughly, where you are, and in turn, you hear them. The whole ocean basin is, for you, a kind of resonant space. It is not empty. It is filled with the slow, patient voices of your kind, and your own voice is one of those voices, contributing to a continuous acoustic chorus that has been going on for far longer than any human civilization has existed. For a whale, time moves differently than it does for a human. A blue whale's call may last 20 or 30 seconds. The pause between calls may be several minutes. A single sequence of calls, a structured communication event, may last for an hour or more. The call from a whale 1,000 kilometers away takes roughly 11 minutes to arrive, the sound traveling at 1,500 meters per second across the water. By the time you hear the call, the whale that made it has moved, has called again, has continued on its slow trajectory through the ocean. The conversations between blue whales are not instantaneous. They are slow exchanges, spanning minutes or hours, with each participant broadcasting and listening across intervals that match the geographical scale of their world. A whale's acoustic life is measured in the rhythms of the ocean itself, not in the quicker rhythms of a mammal living on land. And this is a life that has been going on in essentially the same form for millions of years. Blue whales as a species are estimated to have diverged from their closest relatives several million years ago. Fin whales are similar in age. Humpback whales, somewhat younger. Sperm whales, much older, perhaps more than 20 million years as a distinct lineage. Each of these species has been living its acoustic life in the sea for spans of time that dwarf the entire history of the human family. The calls they produce today are descendants of calls produced by their ancestors. And while the calls have changed and evolved, the basic fact of living inside the acoustic ocean, of depending on sound for communication and orientation and the location of mates and the detection of prey, has been a constant throughout. For tens of millions of years, these animals have been calling through the sea, broadcasting their presence, listening for each other, existing inside a shared medium of sound that no land animal has ever experienced. Think about what it would be like to belong to that kind of acoustic society. To be part of a community whose members you will never see, but whose voices you hear continuously. To know the presence of your kin, not through sight, not through touch, not through scent, but through the ongoing exchange of slow structured calls that travel through the water around you. To feel at every moment the acoustic shape of a world that includes the voices of individuals thousands of kilometers away, as present in your perception as the water immediately around your body. This is what being a whale is like. This is the mode of existence that has been playing out in the oceans of the earth for longer than the human species has been walking upright. And even the smaller acoustic creatures of the sea participate in this, in their own more limited way. A snapping shrimp in a coral reef is surrounded by the continuous percussion of all the other snapping shrimp around it, and its own snaps contribute to that cumulative soundscape. A fish in a spawning chorus hears the combined voices of all the other fish around it, and the chorus itself becomes a signal that other fish further away home in on. Every sound-producing organism in the ocean is embedded in a web of acoustic relationships that stretch beyond the individual, connecting it to others of its kind at whatever distance the physics allows. The ocean, in this sense, is a genuine acoustic community, not a collection of isolated animals making isolated noises, but an interconnected system of acoustic signaling that has been evolving for hundreds of millions of years. And still, we have not reached the full extent of what we don't know about this system. Because for all of the progress we have made in marine acoustics, the so far discovery the whale call catalogs, the hydrophone networks, the long-range propagation experiments, the amount we have actually heard of the ocean, is a tiny fraction of the amount that is actually being produced. We have hydrophones in a few places, mostly in the northern hemisphere, mostly in waters that were militarily significant during the Cold War. There are vast regions of the ocean where no hydrophones have ever been deployed, where no one has ever listened for long periods of time, where the acoustic life of the sea has been going on unrecorded. The Southern Ocean is, acoustically, one of the least studied parts of the planet. The Central Pacific is sparsely monitored. The Indian Ocean has very few long-term listening stations. What is happening in those waters? What creatures are there? What calls they make? What frequencies they use? What patterns of acoustic interaction define their communities? Is largely unknown. We have pieces. We have samples. We do not have anything close to a complete picture. And there are almost certainly sounds in the ocean that have never been recorded, because no one has ever been listening in the right place at the right time. Every year, as hydrophone networks expand and long-term acoustic monitoring continues, new sounds are added to the catalog, some of them matched to known sources, some of them unidentified. The biotwang. A strange three-part sound recorded in the Mariana Trench region was only identified in 2014 and was eventually attributed to a rare species of minke whale, though the attribution is not completely certain. The upsweep, a sound that has been recorded in the Pacific since 1991, is probably volcanic in origin, but has properties that do not fully match any known volcanic source. The sounds come in year after year, and we slowly assign them to sources, and some of them resist assignment, and the catalogue of mysteries slowly grows alongside the catalogue of known sources. There are also almost certainly entire species of whales, and perhaps of other acoustic creatures, that we have never catalogued. This is not speculation. It is based on the regular rate at which new cetacean species have been described by science, even in recent years. A new species of beaked whale was formally described as recently as 2021, based on acoustic and genetic evidence gathered in the Gulf of Mexico. A second new beaked whale species was described in 2023, off the coast of Japan. Beaked whales are as a group among the least known large mammals on Earth. Most of the species have never been seen alive in the wild, or have been seen only a handful of times, and new ones continue to be discovered. Some of them are identified first by their acoustic signatures, by the particular pattern of clicks that distinguishes them from related species before they are ever observed visually. And if beaked whales remain so poorly known, it is almost certain that other acoustic creatures of the deep sea, smaller whales, dolphins, pilot whales, porpoises, and the many species of sound-producing fish, include species that have never been formally described. The acoustic ocean is not a closed catalogue. It is an ongoing discovery process, with new voices appearing in the recordings every year, some of them quickly matched to known creatures, some of them waiting in the archives for the match to be made. Every time a new whale species is identified, every time a new fish chorus is described, every time a new coral reef soundscape is recorded, the acoustic map of the ocean becomes slightly more detailed. But it is never, and probably will never be, complete. The ocean is too large, and its life is too varied, and the creatures that produce its sounds are too elusive for us to ever listen to all of it at once. And there are deeper questions, beyond simple cataloguing, that we have not yet been able to answer. We do not know how many of the whale calls we record carry specific, decodable meaning, whether whale song is a language in any meaningful sense, or whether it is more like an elaborate acoustic ornament. We do not know how far individual whales can actually hear under different acoustic conditions, because we cannot easily measure the hearing thresholds of wild animals in their natural environment. We do not know what most of the deep-sea creatures hear, how the anglerfish, for instance, might perceive the soundscape of the abyssal plain, or whether the giant isopods respond to acoustic cues, or how the hydrothermal vent communities experience the sounds of their own chimneys venting hot water into the cold sea. For each of these questions, we have fragments of evidence. We do not have answers. And perhaps most fundamentally, we do not know what the ocean sounded like before humans changed it. We have only been listening for about 100 years, and for most of that time, our equipment has been shaped by the presence of industrial noise. The true, pre-industrial acoustic baseline of the ocean, what the sea would sound like with no ships, no sonar, no airgun surveys, no offshore industry, is something we can only infer. We can extrapolate backward. We can look at recordings from very quiet times and very quiet places. We can estimate, based on physics and biology, what the ambient noise levels must have been in centuries past. But the actual experience of a whale in the pre-industrial ocean, the quality of the acoustic environment in which baleen whales and toothed whales lived for most of their evolutionary history, is largely lost. It exists only in the bodies and the calls of the animals themselves, who inherited their acoustic adaptations from ancestors who lived in a sea that we can no longer directly hear. Take a moment to sit with that. There is a version of the ocean, the quieter version, the acoustically uncluttered version, that has existed for most of the history of life on Earth, and that we have changed within the span of a single human generation. The whales remember it, in a sense, through the adaptations they carry in their bodies and their calls. But we do not have recordings of it. We did not arrive in time to record. By the time we had the technology to listen, we had already begun to fill the ocean with our own sounds. The quiet sea of the deep past is something we can only reconstruct imaginatively and imperfectly from what we know about the physics of sound and the biology of the creatures that lived inside it. And still, even now, even with all of our noise, the acoustic ocean continues. The whales continue to call. The Sofar Channel continues to carry their voices across the basins. The shrimp continue to snap. The icebergs continue to crack. The earthquakes continue to rumble through the sediment. The deep biosphere continues its slow metabolic whisper. Every moment of every day in every ocean, on every seafloor sound, is being produced and propagated and absorbed and heard by organisms that have been living inside this acoustic medium for longer than any land ecosystem we can name. The sea is not silent. The sea has never been silent. The sea is, in a sense, that is hard to communicate, but easy to feel once you begin to think about it, the most acoustically alive environment on our planet. Keep going, because we are approaching the end. Let's close with a thought that perhaps sits at the center of all of this. The ocean is not only a place of water and pressure and depth and creatures and currents and mineral-rich vents and slow sediment and ancient ice. It is also a place of sound. And the sound of the ocean is not a local fleeting phenomenon, the way sound is in the world above the waves. The sound of the ocean is structural. It is built into the physics of the sea itself, into the way temperature and pressure combine to create the deep sound channel, into the way the water conducts vibration across its vast volume. And because the ocean is so large, and because its physics is so favorable to acoustic propagation, the sounds that occur in it do not stay where they are made. They travel. They cross basins. They connect distant regions. They bind the ocean together in a way that no terrestrial ecosystem is bound into a single acoustic space that extends from pole to pole and from continent to continent, all of it connected. all of it audible to the creatures that have learned to listen. When you look out at the sea tonight, or tomorrow, or at any point in the rest of your life, remember what is actually there. Not just the water, not just the creatures that swim through it, but the sound, the continuous layered ancient sound of the ocean, doing what it has always done, transmitting the voices of its inhabitants, carrying the low notes of distant storms, channeling the rumbles of the seafloor, ringing at every scale, with the acoustic evidence of a world that is far more alive than most of us ever realize. Remember the SOFAR channel, a kilometer below the surface, quietly passing along its signals across entire oceans. Remember the whales, calling into the dark water, broadcasting their presence to other members of their species thousands of kilometers away. Remember the snapping shrimp, producing their tiny detonations by the millions in every warm reef in the world. Remember the icebergs cracking in Antarctica and being heard, weeks later, in hydrophones near the equator. Remember the 52 Hertz whale, traveling alone through the North Pacific, calling in its slightly unusual voice, year after year, detected by listeners it will never meet. Remember that the ocean has been carrying sound like this for as long as there has been ocean to carry it. Remember that the physics of underwater sound is not an anomaly of the sea, but a fundamental property of it, a feature of the planet we live on. Remember that every beach you have ever walked on was the edge of an acoustic world so vast that the world of land-bound animals speaking through air would seem cramped and strangely silent in comparison. Remember that for the creatures of the sea, sound is the primary sense, the main carrier of information about the world. The way they know where they are and who is near them and what is happening beyond the limits of their sight. Remember that we are the visitors. The whales and the dolphins and the shrimp and the fish, they are the natives. The acoustic ocean is theirs. It has been theirs for tens of millions of years, and it remains theirs now, even as we fill it with our own noise. Remember that a sound made in one ocean can be heard in another, days later, thousands of kilometers from its source. Remember that a whale can broadcast its voice across water and be answered sometimes by a voice from the other side of a basin, a voice it will never see, a voice whose owner it will never meet. Remember that the sea is the largest acoustic medium on this planet, and that it carries at every moment an ongoing chorus of signals that we have only recently learned to hear and that we still barely understand. And it is still there, right now, as you breathe, as you rest, as you drift towards sleep. The acoustic ocean is doing what it has always done. Somewhere in the North Pacific, a blue whale is calling, and its low note is entering the SOFAR channel and beginning its slow passage through the sea. Somewhere off the coast of California, a pod of sperm whales is diving toward the deep, clicking continuously, painting the darkness ahead of them with bursts of sonar. Somewhere in a tropical reef, a million pistol shrimp are snapping their claws, producing a continuous crackling percussion that has been going on for all the hours of all the days that reefs have existed. Somewhere in the Southern Ocean, an iceberg is cracking, and the sound of it is beginning its slow passage north, traveling thousands of kilometers through the water. Somewhere on the seafloor, earthquakes are rumbling, and the deep biosphere is whispering, and the hydrothermal vents are hissing, and the whole acoustic structure of the sea is vibrating softly with the continuous input of these countless small voices. And somewhere, alone in the North Pacific, the 52 Hertz whale is still calling, still at a slightly unusual frequency, still answered perhaps by no one, or perhaps by another whale we have not yet detected. Still continuing, year after year, as it has been doing for more than 3 decades now, the simple act of broadcasting its presence into the water. Somewhere out there, right now, that whale is singing. And somewhere out there, right now, a hydrophone is listening. The acoustic ocean is the oldest conversation on Earth. It has been going on longer than any human language. It has been going on longer than any human culture. It has been going on longer than the human species has existed. And tonight, as the world above falls asleep, the conversation continues. The whales call. The shrimp snap. The ice cracks. The seafloor rumbles. The sound travels. And in the channels of the deep sea at the depth of the so far minimum low frequencies glide on and on across the width of whole oceans, carrying voices that will be heard by listeners far away long after the making of them as part of a slow, patient acoustic life that the ocean has been sustaining for longer than almost anything else on this planet. Good night, and may you never look at the sea the same way again.